Let us now in this video have a look at motional EMF, in which I take an example of a rod. So let this be the rod that I have, and I have a wire in this way. So this rod can be moved back and forth, and the remaining wire is just there to complete the circuit, right? So now let us introduce a magnetic field. Let's see, there's a uniform magnetic field that is going through this whole setup, just like that. So I'm drawing these crosses to indicate that the magnetic field is going into the table. So it is going down into the table, the magnetic field, and yeah, it's spread somewhat like this, right? It's spread uniformly in the whole area. And now let us say I use some external agent, which could be my hand or any other force, so external force that is pushing this rod in that direction. Now we know that the area of this, so let me just name the points here. Let me just name it as the book does, PQ, RS, and they've called this length L. So just to be uniform, I'll also use this same symbols, and it's called this distance X. This is X, this is not the magnetic field, this is X, right? A variable. So now I am using some external agent to push this rod in that direction, and by doing so I am reducing the area enclosed by this particular loop. This loop PQRS, the area enclosed by this loop is reducing, and thus the flux through this, so flux is magnetic field times the area. As area is reducing, the magnetic flux through this loop is reducing, and that should induce an EMF. If you find the EMF, we should get, so I'll just use this symbol for EMF. EMF equals the negative d phi by dt. And yeah, in the last video I forgot to tell you the meaning of this negative sign. This negative sign is simply there to indicate that the EMF is generated in such a way so as to oppose the change in flux, right? It is just to indicate this. It has no real this has no such real value. This is just there to indicate that the EMF induces in such a way so as to oppose the change in phi, or change in magnetic flux, right? That's it. So yeah, we'll get some EMF that will be equal to d phi by dt. Now what is phi in this case? Phi in this case, or magnetic flux in this case, is the magnetic field. Let's call that B, the uniform field. So we should get EMF equals minus d. What is phi? It is B times the area, right? Magnetic field times the area. What is the area of this loop? This loop here it's a rectangular loop, so it should be length times breadth, right? And what's the length? The length is x and the breadth is L, so it should be x times L or XL. So B times x times L, BXL, and that is the flux through this thing. And because the magnetic field lines are perpendicular to the plane, we don't need to worry about the angle between the two. It's 90 there. So yeah, sine 90 is 1, so that doesn't count. Now and we get dt there, and now I know B, which is uniform, it is constant. The magnetic field does not change, and L does not change as I move it along in that direction. L doesn't change. What changes is only X. As the rod moves in that direction, X reduces, L stays the same. So I can take X and I can take B and L out because they're constant, and I'm left with EMF equals minus BL and dx by dt. That's visible. Yeah. Now what is dx by dt? Dx by dt is the rate of change of this distance. What is rate of change of distance? Well, it's the velocity of this rod, right? The velocity of this rod is the rate of change of the distance between this point and that point, and that is the velocity of this rod itself, right? If it moves faster, x would reduce faster. If it moves slowly, x would reduce slowly. So dx by dt is nothing but the velocity of this rod. So I can replace dx by dt by simply v, or the velocity of this rod, and but I'm left with this BLV. So I've assumed that I'm moving the rod with a constant velocity, which is V, and so the EMF induced would be equal to minus B times L times V minus BLV, where B is the magnetic field, uniform magnetic field, L is the length of the rod itself, right, this length, and V is the speed at which it is being pushed in that direction. Now that is one way of coming up with the expression for EMF. I could also alternatively come up with another expression, this is the same expression but with another way, and yeah, let me show you that too, just for completeness. What I can think of, so another logical way of thinking about this is, as I move this rod in that direction, the electrons in this rod are also moving in that direction, right? So we are imparting a velocity to all those electrons, right? So the positive charges, the protons and all that, they are fixed in the position. The nuclei cannot move, but electrons can move, and so those so we'll consider only the electrons for now, and the electrons gain a velocity in that direction, and we know that so moving charges feel a force called the Lorentz force, and here that will be given by force equals QVB, right? QV B. B is the magnetic field, V is the velocity of the charges, and Q is the charge on the charge. So because the charge in this case is the electrons are negative, we'll take the opposite direction of velocity, or okay, we'll leave that one now. So the point here is that there'll be some force on the charges, and if I apply my right hand rule, the cross product rule or the right hand rule, I can point my finger in the direction of V, velocity of the charges, so the charges are moving in this direction, and my middle finger in the direction of the magnetic field, which is pointing downwards, and so I should get a force in this direction. But because we are talking about electrons, they are negative, so I also need to consider the negative sign of the electrons. So what I need to do is I need to switch, because they are electrons, so if they were protons they would feel a force in this direction, but because they're electrons they would feel a force in the opposite direction. So actually the electrons would feel a force in that particular direction, so the electrons would feel a force in that direction, so all the electrons will start migrating towards this end. So we would get an excess charge on this side minus negative charge, because the electrons are feeling a force, and you would be left with a net positive charge on this end. So what we can say is that the positive charges have moved in this way. We can say that obviously they don't, and the negative charges move in that end. What actually happens is all the negative charges move, not all, most of the negative charges move in that move towards that end, and we get an excess negative charge there, and we are left with an excess positive charge on this end, and this charge separation causes an EMF, and because we have a wire connected, this current would then flow, and that is what produces current. Now because the charges are moving across a distance of L units, they are moving from one end to the other end. So what we can say is, now this is not a very rigorous proof, not a very perfect proof, but yeah, I'll not get into the exact details of it, but yeah, we can say that the work done in this case, the average work done would be QVB, which is the force, times L, right? What is work? Work is force times distance. QVB is the force, L is the distance the charges move. So this is the work done on the charges, and if we find the work done per unit charge, work divided by Q, W divided by Q, we get so QVBL divided by Q, and this Q and Q cancel, so we can remove them, and we are left with VBL. Now what is work done per unit charge? Well, that is nothing but potential difference, EMF, right? So that can be replaced by the letter EMF. EMF equals VBL, right? And then obviously you can put a negative sign to indicate the direction or the polarity according to Lenz's law. But what we can note here is that again we get the same expression VBL, which we got in the previous in the previous analysis also, BLV or VBL is the same thing, and this is the EMF. And yeah, so that is how we can find the EMF induced in this case when a rod is being moved through a magnetic field. That's it for this video.